So what we're going to do today is we're going to look at something a little bit different. It relates to what we're doing relative to finding areas and things like that. But I read this book about the history of pi. How did they come up with pi? So this is one way that they did it, and you'll see later why it has some kind of relevance to what we're doing. So we have a circle, and inside this circle we have a square, and I'm just trying to get it the right size so that it's actually inside exactly, or close enough. Okay, so what we're trying to do here is we're trying to estimate the circumference of a circle. And if we can find the circumference of a circle that has a radius of 1, so let's say we go from the center of the circle out to the circle, and this length is 1, now we know that the circumference is equal to 2 pi times the radius, but if the radius is 1, then the circumference is 2 pi. So if I can estimate the circumference and divide by 2, I can estimate pi. So the simplest figure that we can do here that would give us an underestimate of the circumference would be to take the square and figure out what the length of each one of these sides is, and then add them together. So the way you do it is you take two lines, one from the center to this corner and one from the center to this corner, and then you draw another one from the center to the midpoint. And what we're trying to do is figure out what this length is here. And if we know this length, we can double it and find the total length here, and then we can multiply it by 4 to get the perimeter of the square. Now, because this whole thing goes through 360 degrees, if I break this up into 8 triangles, because I'll have 2 here, 2 there, 2 there, this angle is 45 degrees. And we know that the sine of 45 degrees is equal to the square root of 2 over 2, and this cosine of 45 degrees is the same thing. So for this simple case, and if this hypotenuse of this triangle, this right triangle, is 1, then L is going to be equal to the hypotenuse times the sine of 45 degrees. Well, the sine of 45 degrees is square root of 2 over 2. In decimal form, it's 0.707 something. So if I take 8 times L, that'll give me the perimeter of the square. So I take 8 times 0.707, and I divide it by 2 because what I'm trying to do is approximate pi. So I take 8 times that, gives me the circumference of the circle, or of the square, but I'm approximating the circle, and that's approximately equal to pi. So pi is the perimeter divided by 2. And if I get my calculator out for that, plug in some numbers. That's my calculator. Okay. We get 8 times 0.707 divided by 2 is 2.828. So 2.828 is approximately equal to pi, which is 3.14. Okay, and we expected it to be an underestimate because, this is inside the circle. Well, the next thing you can do is you can say, well, what if I make a polygon with 8 sides, which is called a octagon? And the way you would create that is you would draw sides now this way. So I take the corners for the square and I just go halfway between and put another side like that. This goes down there like that and up there like that. And so now we have an octagon. And obviously the perimeter of the octagon is going to be closer estimate to the circumference of the circle. So you do the same thing, But if I draw my triangle here, it's going to be half the size because I'm going to go from here to here, and I'm going to go to there, which is 45 degrees. But then I cut it in half to make two right triangles. So I have a right triangle. This angle here is now 22.5 degrees. And there are 16 of those. Just as there were 8 of these, now there are going to be 16 of these lengths. Let's call this L2 for the second time I do it. So L is going to be equal to 1 times the sine of 22.5 degrees. Now the question is, what is the sine of 22.5 degrees? It's not half of that. So how do you figure that out? Well, what you do is you need a half angle formula, and that's typically not taught. You're usually given double angle formula. So I'm going to write the double angle formula, and from that I'm going to derive the half angle formula. So cosine of 2x is going to be equal to 1 minus sine squared of x. So that's the formula. That's the double angle formula because this is double the angle. Now I can also, if I divide the argument by 2, I get cosine of x is equal to 1 minus the sine squared of x divided by 2. So this is still twice that, so it still works. And then what I want to do is solve for the sine of x over 2. So we're going to subtract 1 from both sides. Divided by -1. So now I'm going to take the square root of both sides. So I get the square root of 1 minus cosine x is equal to the sine of x. Oh, and I wrote something down wrong here. So this is 2. So it's 1 minus 2 sine squared x. So this is a 2. This is a 2, so I'm going to divide by 2 here. So the sine of x over 2 is that. So let's just rewrite it. So the sine of x over 2 is equal to the square root of 1 minus cosine of x divided by 2. So let's try that for our particular case. What we want is the sine of 22.5 degrees. And that's going to be equal to the square root of 1 minus the cosine of 45 degrees divided by 2. Okay, so you take 1, the cosine of 45 is 0.707, which is 0.293 divided by 2, and then take the square root of that. So what we find out is that the sine of 22.5 degrees is 0.383. And then if I want to find the cosine of 22.5 degrees, I would find that by using the Pythagorean identity. Sine squared x plus cosine squared x equals 1. Cosine squared of x equals 1 minus sine squared of x. Take the square root, you get the cosine of x is equal to the square root of 1 minus sine squared of x. So for our particular case here, the cosine of 22.5 degrees equals the square root of 1 minus, so the sine of 22.5 degrees is 0.383. We square that. So we take 1 minus 0.382 squared, take the square root of that, and you get the cosine of 22.5 degrees is 0.924. And then you can, if you need to go to the next case, you could say the sine of half of 22.5 is 11.25 degrees is 1 minus the cosine of 22.5 degrees by 2. And you can keep repeating this, so you can keep finding the sine and cosine of the angles that are half 45, half of 22.5, half of keep halving it. So every time you double the number of sides in your polygon, you're going to decrease this by angle by 2, a factor of 2, and you're going to change the sine and cosine. So let's start up Excel here. So I put this all together into a spreadsheet. So the first line is what we've done so far. 4-sided polygon, square. Each angle, each right triangle is 45 degrees. Each right triangle has a 45-degree angle from the center. So there are eight of these sides. Two of each side of the square are. Each side of the square is 2 of the smaller lengths. And the smaller lengths are going to be 1 times the sine of the angle. So if you take this 0.707 and multiply by, well, all we're saying here is that the sine of the angle equals the length of the side L. If you take S times 8 and divide by 2, you'll get that. So you can see I'm taking this side's 4 times 2, which gives it 8. Then I multiply it by the length of each side. That gives me the circumference, and I divide by 2 to find my estimate of pi. And this was my first estimate of pi. The next thing we did was we said I need to double the number of sides on my polygon. So the angle is cut by 1/2, and the sine of the angle is reduced using the half angle formula that I came up with. Then, knowing my sine, I can calculate the cosine. And then knowing the cosine, and calculate the sine at half the angle. And you can keep repeating this to get the sine of the angle and the cosine of the angle. And you can see this length L here, it's this half of this side of the polygon. Keeps getting smaller as the number of sides of the polygon get larger. And as you add all those up, so you take 8 times this number, 8 times this number divided by 2, multiplied by 2, you get that. So this is my 8-sided polygon. My octagon gives a pi estimate of 3.06. And you can keep increasing. So a 256-sided polygon has a estimate of pi of 3.14151381. And you can see over here, this is pi out to 9 decimal places. And you can see after you make a polygon that has 32,768 sides, the estimate of pi is accurate to within 9 decimal places. So what does this have to do with what we're doing? Well, we're trying to figure out circumference in this case, but we are taking smaller and smaller. We're going with a larger and larger number of sides, but each side is shorter and shorter and shorter. And if you took the limit as the number of sides went to infinity, you get the exact value of pi. So that is one of the first ways they came up with getting a good estimate. Their accuracy was basically dependent upon the fact you have to do these calculations by hand, and that's pretty tedious. Okay, the next thing we're going to do is we're going to work a problem. So I'm going to open up Blackboard to get the assignment we're going to work on. So if you look in your calculus folder, you'll see that we have all these in-class assignments that we've been working on. And the one we have here is called Limit Definition Handout. Okay, so let me grab that. So what I want you to do is, we're going to go through another one of these examples using the limit definition. I want you to pause it and see how much you can get done by yourself. I will give you a little bit of introduction here. So remember, the area is equal to the limit as n goes to infinity of the summation from I equals 1 to n of f of x sub I times delta x. So what we're doing is we're finding the areas of rectangles with the height equal to the function and the width equal to delta x. We're going to add up all those rectangles up to some value of n, and then we're going to let n go to infinity to get the exact answer. So delta x is always the upper limit minus the lower limit divided by n. So if this is, say, 10, this is 0, and we have 10 rectangles, you're going to have 10 minus 0, which is 10, divided by 10, which is 1. Each rectangle is going to be 1 unit wide. In our particular case, b is 4. That's x, that's the right-hand limit, and x is equal to 1, and n is going to vary, so we're going to just leave it as n at this point. So delta x is 3 over n. Then you have x sub I, and x sub I is equal to a, which is the right-hand limit, 1, plus I, which is the counter, not imaginary number, times delta x. So you can see when I equals 1, x sub I is equal to a plus delta x. So it's basically starting the right-hand limit, but just moving over to the right-hand side of the rectangle. So this is the right-hand side of the rectangle. So here's my rectangle. Now, if I wanted to do it the left-hand side, the way you do that is you would have x sub I is equal to a plus I minus 1 times delta x. And what that would do is it would we would evaluate the function at the left-hand side of the rectangle. So here we'd evaluate the function, that value, and here we evaluate the function. You find out it doesn't make any difference, and so this is simpler, actually. Yeah, so for our particular case, when I is equal to 0, you get I is equal to 1, which is the first step. You get 1 minus 1, which is 0. And so in that case, x sub I, or x sub 1, is going to be equal to, x sub 1 is going to be equal to a. So that's the left-hand side of the first rectangle. So this way, you do the left-hand side of the rectangle, this is the right-hand side of the rectangle. So we're going to just use this one. So I'm going to go ahead and erase this. Again, it doesn't matter if you do it the left-hand side, the middle, the right-hand side. So for our particular case, a is 1. That's this number right there. So it's 1 plus I times delta x, but delta x is 3 divided by n. So that's 1 plus 3i over n. So that's how I increment the x value. And then I have to evaluate the function f of x sub I. So to do that, you just take this expression and stick it in the function. Well, our function is x squared plus 3x, so it's going to be 1 plus 3i over n squared plus 3 times 1 plus 3i over n. So that's x squared plus 3x. So what I want you to do, just pause the recording, and I want you to plug in f of x sub I here, plug in delta x into there, and then multiply out this term. So you're going to use FOIL, 1 plus 3i over n times 1 plus 3i over n, and you'll get terms that involve I squared, terms that involve I, and terms that just involve a constant. And then you can group those together. And at that point, if you get to that point, go ahead and stop and see if you've done it correctly. Okay, so either you've gotten what you think is right or you're not sure what to do. So let's go ahead and do it. So the area is equal to the limit as n goes to infinity of the summation from I equals 1 to n. So for f of x sub I, I'm going to put in 1 plus 3i over n squared plus 3 times 1 plus 3i over n. And that whole thing is going to be multiplied by delta x, which is 3 over n. So the first thing to do is to just multiply this thing out. So you're going to have, you're going to have 1 times 1. Then the second term is going to be this times 1, but it happens twice because you have inner and outer. So what you get is 2 of those. So you'll get 6i over n. 3i over n plus 3i over n is 6i over n. Then you multiply these two together. So you get plus 9. 3 squared is 9. I squared is I squared divided by n squared. Okay, so that's this one. And this one is going to be 3 times 1, which is 3, and 3 times this second term, which is going to be 9i over n. And that whole thing is going to be multiplied by 3 over n. And I'm leaving off this stuff for the time being. So the next thing you do is you're going to combine like terms. So 1 plus 3 is 4. 6i over n plus 9i over n is going to be 15i over n. And then you've got 9i squared over n squared. And that's multiplied by 3 over n. And then the final step is to multiply this out. So 4 times 3 is 12. So we get 12 over n plus 45. 15 times 3, 45i over n. And then 3 times 9 is 27. 27i over I squared over n squared. Okay, so let's plug it back in now here. So the area is equal to the limit as n goes to infinity of the summation from I equals 1 to n of 12 over n plus 45i over n squared. Oh, this is just 12 by itself. No, it's 12 over n. I've got a problem here. I made a mistake down here. So this is n squared. Let me fix this. Okay, sorry, I forgot to divide by n. So here we get 12 over n. I think I did that right. Then you have 45i over n squared, n times n, plus 27i squared over n cubed. Okay, so that's what I have. So now what we're going to do is we're going to make this into 3 separate summations. So we're going to take the limit of this whole thing. We'll have the summation from I equals 1 to n of 12 over n plus the summation from I equals 1 to n of 45i over n squared plus the summation from I equals 1 to n of 27i cubed I squared over n cubed. Now, I'm going to factor out some terms here out of the summation. So we're going to have 1 over n times the summation from I equals 1 to n of 12 plus, in this case I'm going to factor out 45 and n squared. You'll see why in a second. And what that leaves is the summation of I from I equals 1 to n. And then the last one here, we're going to have 27 divided by n cubed times the summation from I equals 1 to n of I squared. So we had these summation formulas that said the summation from I equals 1 to n of c, some constant, which is c times n. The next one was the summation from I equals 1 to n of I was equal to n times n plus 1 over 2. And the other one we need is the summation of I squared. And that, I don't remember, so I'm going to have to look it up. It's like n times 2n plus 1 times something or other. Okay, here it is on page 260 in your book. So this one is n times n plus 1 times 2n plus 1 divided by 6. Okay, so those are the formulas that we were given. So what I'm going to do is I'm going to do each one of these separately and use the appropriate formula. So the summation of 12 from I equals 1 to n is just 12n. So c is 12, so it's cn. Okay, that's easy. The second one is the summation of I from I equals 1 to n. And I've already got it up here, but I'm going to go ahead and multiply it out. So that's what I get. I get n squared plus n over 2. And then the third one, I squared. So what happens is you get n squared plus n. That's multiplying this by that. And then you multiply by 2n plus 1. And then you divide by 6. And then you multiply it out again, so you get 2n cubed. So this is first. Outer you get 1n squared, and inner you get 2n squared. So it's plus 3n squared. And then last is n. So that's what you get from that part. So what we can do is go over here now. So we get rid of the summation signs. Take the limit as n goes to infinity. So we have 1 over n times this thing, which was 12n. Then we have 45 over n squared. And then we multiply by this, which is n squared plus n divided by 2. And then the final one is 27 over n cubed times 2n cubed plus 3n squared plus n, all divided by 6. Now before we take the limit as n goes to infinity, we're going to simplify each one by trying to cancel out stuff that we can cancel out. So here we have n divided by n is just 1, so you get 12. Here we'll get 45 n squared divided by 2n squared. And then the second part we'll get 45 n over 2n squared. And then the last one we'll have 27 times 2, which is 54. 54 n cubed over n cubed. Second thing, we'll get 27 times 3, which is 81. So it's 81 n squared over n cubed. And then the final one is just, and I got to remember to divide by 6. I almost forgot that last time too. Divide by 6. Everything has to be divided by 6. Okay, then you get 27 times 1, so you get 27 n over n cubed. Okay, one more time, one more level of simplification here. Take the limit as n goes to infinity of 12 plus, well, these cancel out, 45 halves. This cancels out one of those, so you get 45 halves times up. Yeah, that's right. Plus 45 halves times 1 over n. So that becomes 1 over n. Then you have n cubed divided by n cubed. So you get 54 over 6 plus 81 over 6. I forgot the 6 here again down there. 81 divided by 6 times 1 over n. Because n squared, cancel out with n squared there, just leaves 1 over n, plus 27 divided by 6 times 1 over n squared. So when you take the limit as n goes to infinity, that goes to 0, that goes to 0, that goes to 0, and all we're left with is 12 plus 45 halves plus 54 6. So let's do the fraction stuff here. So we'll leave them as 6 because I could simplify that, but we need to make them as 6 to make this thing work out. So 12 is equal to 72/6. So you multiply this by 6, get that, divide by 6. This one you have to multiply by 3, so 3 times 45 is 135 over 6, and 54 over 6. And if you add all those together, 72 plus 135 plus 54, you get 261 over 6. And you can divide 261 by 3, it's 87. So you get 87 halves. So that's the answer. So you can turn that paper in. And what is that? That's the area. Get so caught up in the nitty-gritty stuff here. So the area is 87 halves underneath that curve. Let's actually just look at the curve. So here's the graphing program. So the function was, what was the function? X squared plus 3x. X squared plus 3x. So there it is. And what we're doing is we're looking for the area underneath the curve between 1 and 4. So if I drew a vertical line here, come over to 4, draw another vertical line, it's the area here from the red curve down to the x-axis. And calculus tells us that that area, 87.5. Now, I'm going to demonstrate something. What if you took the antiderivative of x squared plus 3x? So use the rules. The integral of x squared, you add 1 to the exponent, divide by the new exponent. You add 1 to the exponent, divide by the new exponent. Add your arbitrary constant c, but I'm just going to let c be 0, just because. Now if I evaluate the antiderivative, I'm going to use a capital F at the upper limit I'll have 4 cubed over 3 plus 3 times 4 squared over 2, which is 4 cubed is 64, so I get 64 thirds, plus 16 times 3 is 48, so I get 48 thirds. And if you add those together, 64 plus 48, you get 112. Oh, sorry, you got a half, 2 here, so it's 48 over 2. Okay, so let's try that again. 16 times 3 is 48. Okay, so let's convert it to sixths. So 64 over 3, if we double that, we get 128 over 6. And if we multiply that by 3, 48 times 3 is 144, so we get 144 divided by 6. You get 144 plus 128, you get 272. Something's wrong here. Okay, let's go back here. Let's see, 16 times 3 is 48. And 4 cubed, 64. 64 times 2 is 128. 48 times 3 is 144. So what am I doing wrong here? Something's not working out. Oh, no, that's okay. So that is, I forgot I'm subtracting something here. So, okay, so you get 272. 272 over 6. Okay, now if we evaluate the antiderivative of 1, we get 1 cubed over 3 plus 3 times 1 squared over 2. So that's 1/3 plus 3/2 in terms of sixths. That's going to be 2/6 plus 9/6. That's 11/6. So if I take the antiderivative evaluated of 4 and I subtract the antiderivative of 1, I get 272/6 minus 11/6, which is equal to 261/6, which is equal to 87 thirds, which is the same answer I got using the limit definition. 87/2, sorry, which is the same answer. Okay, we'll find out later, actually in the next lecture, that this is what the fundamental theorem of calculus tells us. It says the area calculated using the limit definition is the same as the value, the quantity you get by evaluating the antiderivative of the original function at the upper limit and subtracting the antiderivative at the lower limit. So you can go ahead and turn that in. I think that's pretty much it for that. What we'll do next time is we will do some antiderivative stuff just as a review, and we'll introduce the fundamental theorem of calculus and a few other things. Okay.